We're moving right along into Unit 3 from periodicity to chemical bonding. And it does overlap, and that's why it leads into bonding as we go from periodicity. Much of it is in the electronegativity values and the trends for electronegativity. This should look familiar to some of you. This is a chart that describes, big picture wise, what are the 4 types of bonding. And they are covalent, ionic, metallic, and covalent network. And some of the types of elements that make up those bonds, as well as nature of bonding electrons, forces of attraction, intra versus intermolecular forces, the unit, as well as the Lewis structure, and then, of course, the macrostructure, which is the bulk made up of many, many, many particles or atoms or molecules. Go ahead and study this whole chart. Read it over and make sure you can see the big picture of this whole unit as we proceed. This chart continues over here with melting points as well as conductivity, testing, brittleness, and vapor pressure, surface tension, and states of matter. And notice how you see covalent compounds have varying states of matter. And then, of course, as you get into ionic, metallic, and covalent network, they're all very tightly held together particle-wise, and they tend to be solids at room temperature. So once again, the lead-in from the previous unit is electronegativity, and by the definition of electronegativity, the ability for an atom to attract another atom's valence electrons or electrons, it seems suitable that electronegativity is used in bond types and bonding. So we can use the difference, the electronegativity difference, these are all the values, and we can use that as a way to guide us, not always definitive, but guide us through whether the bond type is nonpolar covalent or polar covalent or ionic. And so these are the difference of electronegativity between the 2 atoms that are bonded. And this will tell us what type of what bond type. Now it doesn't go into metallic, it doesn't go into covalent network, but it really sticks to this electronegativity chart is used for both covalent and ionic. And the types of elements we saw earlier as well. Just review and make sure you understand you can actually look at the bond, the electronegativity difference to determine the bond type. The first type of bond we will venture into is covalent bond, and that's because covalent bond is quite extensive. Sharing of electrons, we see lots of different shapes that come out of it, as well as different types of intermolecular forces that occur. Let me emphasize the word inter versus intra. So here shows a big macrostructure of HCl, hydrogen chloride, and between the 2 atoms is the true bond, the covalent bond that's occurring between carbon or the hydrogen and chlorine, and that is an intra. So it's within. Within means intra. Now, I'm going to circle that and say that's within. Now, inter means between. So this is a force that's occurring between the particles. And you're seeing that as HCl is attracted to another HCl, and this is an attraction between. Usually the between forces are dotted lines, whereas the intra is a solid line when it comes to covalent bonds. Okay. The term molecules used for covalent bonds, don't forget that I never use it on ionic compounds nor metallic. Molecule is strictly for covalent. That's actually a very good clue that it's covalent as well. Covalent compounds are guided by sharing of electrons between nonmetals. Their attractive force is called their intramolecular force, and it's measured by something called bond energy. We'll see that chart of bond energy soon enough. Attractive force between particles is called intermolecular forces, and these are weaker. They actually are these intermolecular forces are actually what guides the melting point and the boiling. So when we melt a covalent compound or boil covalent compound, we're actually breaking these intermolecular forces. We're not actually breaking the intra, we're breaking the inter. And that's why melting points and boiling points are guided by these intermolecular forces. Covalent compounds tend to be gases, liquids, or solids. Low melting solids, though, at STP. Non-polar covalent are insoluble in water because water is polar, while polar is soluble in water because polar dissolves in polar. Like dissolves like. Unlike does not dissolve each other. So these two are unlike each other in polarity. Nonmetals are poor conductors of heat and electricity. There are 7 diatomic. Know the 7 and where they're located. They make this lovely number 7 plus hydrogen, and there's 7 of them, okay? Know where they're located. All right, so let's go over covalent compound bonding and their potential energy. In example 1, we're looking at internuclear distance and potential energy. So this chart I'd like you to really look at and become familiar with. It's this idea that there's a certain distance, optimal distance, between the nuclei of both atoms where the atom will bond for one, and the atom will meet this low potential energy. So this low potential energy is a stable bond, a stable state for the two atoms that are bonded. Now, if you increase the distance between the nuclei, so you're increasing the internuclear distance, you'll see those two atoms they are too far apart. They're too far apart to basically attract each other and bond. Now, if they're too close, there's such repulsion occurring, and so you're going to not see them bond at all. And that is a high potential energy, which means that particle will not exist because low potential energy means stable particle, high potential energy means it's an unstable particle. In a covalent bond, the bond length is influenced by both the size, which is Coulombic law, of the atom's core, uh, and the bond order, so single, double, or triple. So you're going to see in a single bond, like HH here, that the bond um, length is going to be farther apart than a double bond. A double bond will be closer together, and of course the shortest bond length is going to be between a triple bond. So bonds with higher order, in other words, single versus double versus triple, are shorter and have higher bond energy. To break a triple bond requires much more energy than to break a single bond. That is that relationship you're seeing. So here you see you're asked to match X2, Y2, and Z2. These are diatomic molecules to the bond order. So you're looking to see which one would have the double bond versus triple versus single. And if you look at the internuclear distance, you'll notice that the one with the smaller internuclear distance is probably the triple bond. So this one's the bond order of 3. So bond order is like this: 1 degree, 2 degree. Looks like degrees, but it's just bond order here. So x squared is a triple bond for sure. X to the y2 is actually a double bond, and then the last one is a single bond. So those are your bond orders. Moving down to Lewis structures, you've got to read these important general guidelines, and they are in priority order. So, number one, you want to make sure you follow and do first. This is all about drawing Lewis structures for covalent compounds and making sure that you follow this order to ensure that you never make the mistake of drawing these Lewis structures. So please read it and make sure you follow from here on out this order. If you need to go back to it, please do, to constantly know the order. All right, the rules continue all the way to number 7 right here. The new part, so you've learned already in chem how to do all the way to 6. The new part is the 7. So I'd like to really stress the new part, which is new to you all in AP. Acidic hydrogens are always most likely to be attached to a more electronegative atoms. So the more electronegative atoms are your atoms that are F, O, or N. So Phan. Also NOF. Some people like to use NOF versus Phan. I like to use Phan. Cyclic structures. Oh, sorry. So basically, hydrogens will always attach, acidic hydrogens will always attach to these 3 elements here. Cyclic structures are stable in pentagons, hexagons, and heptagons. Triangles and squares are not stable due to angle strain within the structure. So you will not see cyclic structures of triangles and squares unless they're TNT, so something that is explosive, unstable basically. But most of your stable structures in nature are oftentimes pentagons, cyclic structures that are pentagons, hexagons, and heptagons, or octagons, so on and so forth. Nonagons as well, or decagons. But ultimately, anything 5 or above in terms of 5-sided structures. You want to try to minimize your formal charge in your structure, especially around your central atom. You won't usually see your central atom have a formal charge, with certain exceptions, but for the most part, they don't carry on formal charge. The net charge is usually carried by the electronegative bonded atoms. So usually, when you see a net charge for, say, a polyatomic ion, that charge is due to a formal charge on the bonded atoms, not the central atom. And then last, you use oxidation numbers to determine the valence electrons involved in bonding. So we will get into this understanding that at times you're going to have to assign oxidation numbers to understand that that number represents the valence electrons involved in bonding in that structure. And then last one, organic formats are branched. So you'll see this branching that you see here. Most of your organics look like this. And each corner of the branch chain represents carbon. So notice how there's 1, 2, 3, 4 carbons. So here's 1 carbon at the end. Here's a carbon right here, and a carbon right here at the ends. So this branch structure really matches this Lewis structure, or this long branch structure also here. So they look alike. Notice the oxygen right here and the oxygen right here. Likewise, this structure right here, this is the organic branch structure that you see. They like to put it this way because it's a lot cleaner, simpler looking, as well as just easier to handle and draw for one. Okay, so that's why they like to use these branch structures. And organic compounds, when we say organic, it's all elements that are your nonmetals: carbon, oxygen, nitrogen, phosphorus, hydrogens. Those are your organic compounds. So let's look into example 2. You're drawing the most stable Lewis structure for each, and you're counting the number of pi and sigma bonds for each structure. I haven't gone over pi's or sigmas yet, but sigmas are your single bonds, and then pi's are your double bonds or triple bonds, okay? We'll practice some, and then you'll get the idea of how to count the pi's and sigmas. It's quite easy and straightforward, and you'll read it also in the Lewis structure rules. Okay, let's draw the Lewis structure for ethene. Ethene is made up of 2 carbons and 4 hydrogens. I'm going to start off with first drawing the carbon. And because there's 2 carbons, I know those 2 carbons are your central atoms. So some structures have several central atoms. And once again, I draw the valence electrons for carbon. And I then draw my 4 hydrogens that I have. I'm going to symmetrically divide them on both carbons. So I'm going to put 2 hydrogens. And I like to put the hydrogens where I can bond them pretty easily. And then I'm ready to do all my single bonds. And then at this point, I look at the structure and I see that I don't have my octet yet for both carbons, and I can see a multiple bond come out of this that would allow me to have my octet. So I check my octets. 2, 4, 6, 8. And so this structure looks good on that carbon. And then I check the other octet, 2, 4, 6, 8. And so this carbon looks good. And hydrogen has a duet, and it looks like that's the case. So 2 here, 2 here, 2 here, and 2 here. Okay. Moving on to B. In letter B, you have the organic branch structure that you see right here. So you're going to draw the Lewis structure. And you're going to need to really draw small, okay, because there's a lot of atoms. So the first one that you see here is carbon. And you know that there's 4 dots. And you know that that carbon is attached to, I'm going to label this carbon number 1, 2, 3, 4, 5, 6, and 7. That way you can follow my carbons, okay? So this is carbon number 1 that I have right here, carbon 1. And then I know that there's another carbon. And then I know that there's an oxygen. Now where I don't see anything else other than, or where those corners are carbon, I know that there's hydrogens attached to those carbons, okay? And then again, you'll get good at this where you don't need to do the dots. So you actually can cut a few corners. But for now, we're not going to cut corners. So here's my 3rd carbon. I'm on my 3rd carbon. And that 3rd carbon has an oxygen on it. Going on to my 4th carbon. And then my 5th carbon. And then my 6th carbon. And then my 7th carbon. Okay. Now notice I drew all the dots. I know there's hydrogens in between, and I can even I can even start connecting my carbons together if I'd like, because I know there's that connection along the stretch there before I put the hydrogens in. The hydrogens will start to clutter this structure, and that's why the branch structure is so popular. All right, so now I'm also going to probably erase at times as well. Okay, so now here I have a hydrogen and another hydrogen bonded right here, and another hydrogen. So there's 3 hydrogens on carbon number 1. I know that there's 2 hydrogens in carbon number 2. And then there's nothing going on. There's an octet on the oxygen. so I can skip over to this carbon. Now I also know that there's a double bond because I see a double bond between the oxygen and the carbon here. So I'm going to erase, and what I'm going to erase is this electron. I'm going to bring it up here, and then I'm going to double bond right here because I see an unpaired electron on oxygen. And I'm going to erase. So I'm going to erase that electron, and I'm going to move it right here, and this is what allows me to double bond between the oxygen. Notice the oxygen now has an octet. Now I go down over to the next. I see between carbon number 4 and number 5 is a double bond. So I know I'm going to have this double bond between the two atoms. But I also, and that will tell me that these two bonds, or the bottom two unpaired electron, is where hydrogen is housed. So now between carbon number 5 and 6 are single bonds. So this is a single bond. I know there isn't any more than that, but I know there's a double bond here. So I'm actually going to double bond so I can see how many hydrogens will come out of between the 6 and the 7, carbon 6 and 7. And now I can see where the rest are hydrogens. Okay, I hope that makes sense. Once again, you can label the carbons afterwards if you want, or along the way. I just didn't have any room. And if you label it, that could help you track which carbon is which off of the branch structure. It doesn't, technically you do not have to have those carbon numbered in the structure. All right, let's go to the next one. Now, feel free to pause and try the problems out yourself if you'd like to. You're more than welcome to. Please do so. Pause and try it out. The next structure, I know my nitrogen is going to be my central atom because it's the least electronegative, and I know that there's 3 oxygens, and because this is an acid, as it says right here, it's nitric acid, I know my hydrogen, as stated up here, is going to be attached to the more electronegative atom, and it could be any of these 3, okay? So it's got to be one of these oxygens. That's where my hydrogen has to be attached, according to what I see up here. So I've decided I'm just going to put it on any of the oxygens, okay? The oxygen on the right. Now, nitrogen has 5 valence electrons. I'm going to draw that in. Oxygen has 6 valence electrons. Drawing that in. Okay. And then I do all my single bonds. So then I can assess what to do next. Now I see that this oxygen does not have an octet. I see my nitrogen have an octet. I see this oxygen does not have an octet yet. So these 2 oxygens do not have its octet, whereas this oxygen does have its octet, and the hydrogen has the duet. So I'm going to have to play with these structures. Now I know you're tempted to say, hey, Mrs. No, I see an unpaired electron here and I see an unpaired electron here. Why don't I just move one over the other side and bond them? But if you bond them, now you have a triangular cyclic structure. And we said that cyclic structures that are triangles are not stable. So probably not going to happen for this structure. That's pretty stable. Nitric acid is a pretty stable acid that we use in chemistry to do experiments. So our next plan is to probably have to break this unpaired or this lone pair right here to try to achieve an octet for both these oxygens because they cannot exist like this. So to break it is for me to change some positions. I'm going to change the lone pair of the oxygen on the top, and I'm going to move that oxygen's lone pair on the bottom right down here. And then, so now I have an unpaired up here. I'm going to do a multiple bond. Now, upon doing the multiple bond, I notice that my oxygen has an octet here, but this brings about some problems with nitrogen. Now nitrogen has 2, 4, 6, 8, 9. 9 is too much. And then let's assess this oxygen. I have 2, 4, 6, 7. 7 is too little. So 9 here, 7 here. How do you make 8 each? You are correct to think that this electron will move over to here. And logically, it makes more sense that that electron would hang around oxygen, because oxygen is more electronegative than nitrogen. So I'm going to erase that electron, and I'm going to move that electron over to here. Okay. Now, erasing that means my formal charge of nitrogen is going to be +1. It's lost an electron. While this oxygen has gained 1 electron, so the formal charge is -1. Now, although you're going, but Mrs. No, don't you want to minimize formal charge? Yes, you do, but octet seems to always be an overriding rule compared to minimizing formal charge. So now we have octets on all the atoms as well as a duet on the hydrogen. So this is the best Lewis structure for nitric acid. Let's go ahead and look at cyanic acid. Cyanic acid, unusual as it is, it's an acid, but the hydrogen actually is going to have to be on the carbon, not the nitrogen. Let's test this out. Now, if you want to put that hydrogen on the nitrogen, I want you to test out to see what would happen. If you played it that way, you'll notice that carbon's going to make some really interesting bonds, and it's just not going to logically occur, and carbon couldn't do that. So the best thing for us to do is to make your single bonds here, your sigma bonds, and then do your pi bonds afterwards. So there you go. All the atoms are octets or duets. Now I want you to go ahead and work through the rest of the problems. I do apologize. I'm supposed to count sigma and pi bonds with you. So sigmas are always your single bonds, okay? So here's my single bond, 1, 2, so 2 sigma bonds. And then there's a single bond that really is the initial bond between the 2 carbons, so that's 3, 4, 5. There's 5 sigma. Pi bonds are double bonds. So they actually occur on unhybridized p orbitals, which you won't know until we'll get into that a little bit more later on. So in terms of sigma bonds, there are, as we counted, 5 sigma bonds, and then pi bonds, there's only 1. Okay. Wow, this structure has a lot going. So sigma bonds and pi bonds. Let's count how many we have of each. It's nice to have the Lewis structure because now you can count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There are 18 sigma bonds. Pi bonds, let's count them. Here's a pi bond, 1, 2, and 3. So there are 3 pi bonds. Sigma, if you count carefully, you should see 1, 2, 3, 4. Pi bonds, you see 1. In this structure, be careful. Sigmas, you see 2. Pi bonds, because there's a triple bond, there's 2 pi's. So there's 2 there. Go ahead and work through the rest of the problems and practice. The answer key is below. All right, let's talk about resonance. Resonance is only through experimentation that we discovered that particles like ozone, their bonds are identical. In other words, this bond right here is identical in energy when we break it versus this bond on this right side for ozone. This is ozone right here. And with that discovery, we understood that there exists resonance structures. And basically, resonance structures are other possible Lewis structures where the pi electrons, this double bond right here has a pi electron and a sigma electrons. The pi electrons can resonate over to the other side. In other words, it can move over and relocate onto the other side of the bond as long as they're the same exact bonds. So it's OO bonded here, OO bonded here. So this pi electron can resonate over to this side. And resonance occurs because those pi electrons are delocalized. They're delocalized electrons, just similar to the electrons that are in metallic bonding. These pi electrons are delocalized on unhybridized orbitals, which we'll talk about later on. But ultimately, that delocalization allows those pi electrons to move around the entire molecule, distributing to make equivalent bond order or effective number of bonds. So let's talk about ozone for a second. Ozone has this pi electron that's being shared over to this side. So if you split up that pi electron between these bonds, you will have one sigma bond plus half a pi bond. So we use the idea that the pi electrons delocalizing around the OO bonds of both resonance structures that you see here. So there's two resonance structures where the pi electron moves over to this side to create this resonance structure. The bond order is 1.5. How I usually compute bond order is as such. I usually take the total number of bonds, so there's 3 total bonds, 2 sigma and 1 pi, and I divide it by however many bonds or however many bonded atoms bond around to the central atom. So there's 2 bonds to the central atom. The central atom being oxygen, there's 2 bonded atoms. So then I split and see that in the end it's 1.5. So 3 halves is technically 1.5. So the bond order is 1.5. What we're going to do now is we're going to draw the Lewis structures, and we're going to draw all the resonance structure, and then we're also going to calculate the effective number of bonds. So drawing the first one, this is nitrite. So it's NO2 with a minus. It's kind of hard to see that minus, but it's nitrite ion. Drawing nitrite ion, we start off with the central atom, nitrogen. Once again, I draw all the valence electrons for that central atom. And then we draw the 2 oxygen atoms. And I'm going to spread them out away from each other because bonded atoms, like electrons, are full of electrons, and thus those bonded atoms like to be away from each other as possible. So now oxygen has 6 valence electrons. Again, I do my single bond, and then I realize that there's not enough octets around each of my atoms, so I do my multiple bonds. Ooh, I forgot. I'm going to add an electron where I need to add an electron because this negative symbol right here, this negative on the nitrite ion means I'm going to add 1 electron. So I'm going to add an electron, and where it needs it the most is where I'm going to be noting where I'm going to add it. So it looks like electrons usually are drawn to bonded atoms more so than the central atom. We said that the central atom doesn't usually take on formal charges, usually. So I'm going to put a negative formal charge right here because you've added an electron right at this spot. And then I'm going to do my multiple bonds, and it looks like I can get a multiple bond between nitrogen and oxygen. And thus, it looks like everything has an octet, oxygens and nitrogens. Check and make sure. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So you're always checking, eyeballing, and make sure you're checking the structure. Now, this structure has a negative charge, and we tend to put a bracket around this with a -1 charge outside. So we show that there's an overall charge to this ion. Now we're drawing resonance, so I apologize, I really didn't give myself enough room, but I'm going to squeeze in here. So my pi electrons can move over to the other side, and when I do that, and I'm going to take some shortcuts, my lone pair is going to look like a line instead. And then, of course, where the double bond, I see 2 lone pairs, and I'm going to situate those lone pairs as far apart from each other as possible, along with my bonded and pi electron as well. And this is my resonance structure here. So there's 2 structures. I would draw small for my initial structure so that I can draw my resonance structures in. So here's where my -1 charge is. And again, overall, the charge of the whole ion is negative. So I'm going to put a bracket on the outside and a -1 charge. Sorry, you're really tight in space here. But go ahead and draw carbonate ion, which is letter B. Work through letter B and letter C. Answers are on the bottom. You can check for all the resonance. Oh, I forgot to do bond order for nitrite ion. So bond order, once again, I see that there's the nitrogen is bonded to oxygen, so there's obviously one order, bond order, the sigma bond basically. And then of course the pi electrons are going to be shared between the 2 nitrogen-oxygen bonds, so it's a 1.5 bond order. So I'm going to write that in, 1.5 bond order. Go ahead and do the rests and check your bond order as you go through each of the different bonds in that structure. And pause to do that because I'm moving on to the next section. Otherwise, pause to do work through B and C. All right, let's go into formal charge. Formal charge is basically it's designated charges in a structure that's covalent. And usually you're looking at basically the electrons, valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. And so you're taking that difference. This is the equation to calculate formal charge. Number of valence electrons in the free atom minus the number of electrons assigned to that atom. We'll talk about what it means by assigned to that atom after we do a couple of examples. The best Lewis model can be determined among several resonance structures as the one with the least formal charge and has an octet. So you're looking at the best, most stable Lewis structure to have less formal charge as well as an octet for all the atoms. And duets if it's hydrogen, okay? Let's go ahead and look at this example. We're going to look at formaldehyde as our first. And it says to draw at least 2 possible Lewis structures assigning formal charge and use justification as to why which one is better than the other. We're going to do formaldehyde first. All right, let's go ahead and do A. I'm moving on to the next page so we have space to draw the Lewis structure for A and assign formal charges as well. Okay, we start with carbon. And we know that oxygen has 6 valence electrons, 2 of which are available for bonding. They're unpaired, so they're available for bonding. And that means the other 2 are going to be situated on the other sides. So this is, when I'm drawing, I'm always prepared to think about where the bonding will take place. So I do my single bonds. And then I double up because carbon and oxygen must have an octet. Okay, and so in this structure, let's go ahead and assign formal charges. I'll do it in red so you can see. And I'm going to count so you can see also, okay? So oxygen as a free isolated atom has 6 valence electrons. This is not including the one bonded. We're talking about just strictly the valence electrons. So when you draw the dot for oxygen, that is 6 valence electrons. So that is the first part of calculating formal charge, taking 6. Now, the number of electrons assigned to that atom is just really saying, okay, how many now do I see when it's bonded here? So accordingly, I see 1, 2, 3, 4, 5, 6 that is on the oxygen in this structure. So once again, all I'm doing is subtracting 6 minus the 6 that's assigned to that atom, and so the formal charge is 0. Likewise, for hydrogen, I see 1 valence electron and 1 assigned to the oxygen, so it's 0 here. And the same goes here. 1 minus 1 is 0. So both hydrogens have a 0, 0 formal charge. Now let's draw another structure for formaldehyde. Once again, I'm putting the oxygen on this side, but I'm going to do something a little different for this oxygen on this side, okay? Sorry, I should lay it out exactly how it looks from the previous, and that means having the unpaired electron on the bottom, not the top. All right, so go ahead and draw our sigma bonds. And then instead of doing a double bond, I'm going to move this electron over here. Now moving this electron over here is going to now erase this electron, and now I'm going to add that electron over, and I'm going to add it in red so you can see the newly added electron over to oxygen. And so in this structure, now although this structure doesn't give the carbon an octet, that is a combination of why this structure isn't the best Lewis structure for formaldehyde. But let's add to the rationale that it's not a good structure because of the formal charges. So let's go ahead and add formal charges. Again, 6 valence electrons. If you were to draw purely oxygen's valence electron in the free atom, and then currently what you see in the structure, you see 7. I wanted to show you how you see the word assigned. I see 7 electrons assigned to the oxygen. So let me count it for you. 2, 4, 6, 7. So that's the 7, okay? 7 assigned to that atom, so that's why it's minus 7, and so the formal charge is negative 1. Logically, it makes sense. The negative 1 right here, the oxygen has gained an electron from the carbon, so that's why the negative 1 stands to make sense here in the formal charge. Now let's do all the other atoms and calculate the formal charge of all the other atoms. So 4 minus, and I only see 3, so it looks like plus 1 is the formal charge around the carbon because carbon lost an electron. And if you calculate both hydrogens, you'll see that's 0. So notice how this second structure has greater formal charge, and it violates the octet rule for the carbon, so you know this structure is not a stable structure. So what I'm trying to show you is you can eliminate structures, Lewis structures that are not great or not stable or not ideal because they have formal charges and violates the octet rule. So go ahead and work through these other examples. these two other examples, draw all the possible Lewis structures, and then give rationale as to why one structure is better than the other. All right, pause and do that. Let's go down to structural isomers. Structural isomers are molecules that have the same molecular formula but different structural arrangement. Here's an example: butane, C4H10. Butane, if you can see right here, it's got 4 carbons and 10 hydrogens, as you see tallied up. But then when you then take one of the carbons and put it in the middle of the structure, now you have the same formula. So notice it's C4H10 still, but the structure looks different. So the structural arrangement is different than this long branch structure right here. So these are called isomers, structural isomers. The same formula, however, different structures. Tonight's homework is to work through the supplemental worksheet that will be linked in this document. I'll add a hyperlink right here for the AP Lewis worksheet, and a key for you to check your answers. Please make sure you practice drawing it out, all these structures, and then you check with the key afterwards. I'm also going to add another link for reviewing these different molecular geometries. There's going to be 2 links. One is a PhET that allows you to create these structures through a simulation, a PhET simulation. And the other one is going to be my video that I offered. It's the same video that I had given out for Honors Chem, and it shows how I build these candy models to help me to visualize these different shapes. My recommendation is to buy some dots if you have dots, or a grape, and get some toothpicks and start building at home. It's nice to use dots because you can reuse the dots itself, and a small package goes a long way. By the way, well, Halloween is coming up, but it's way too far away for us to be able to save those dots from Halloween, and I'm not sure how Halloween is going to look this year. Either way, go ahead and get yourself some toothpicks and something for your central atom, and go ahead and build these different geometric shapes, not only through the animation PhET as well as the video. So I'll leave it right here for you in your notes. So the VSEPR theory stands for valence shell electron pair repulsion. Exactly what you see here. The electrons in the valence shell will repel each other. Now, obviously, they also repel each other in the core electrons as well, but really ultimately we're looking at how the valence electrons repel each other in order to make these different geometric shapes that we will see along the way. It's important to really understand the root shapes as you're going through, so please make sure that you study the root shapes and all the derivatives that come off of the root shapes. So here are the root shapes. This is the column for it, and these are all the derivatives that come off of that root shape. Both the PhET as well as the video should help you really nicely, and then of course the big part is creating your own geometric shape and visualizing it yourself. So please take some time to do that so that you can work through the worksheet as well. Continue on. Once again, these are all root shapes, and these are all the derivatives following those root shapes based on your VSEPR theory. Go ahead and work through this problem. There's obviously an answer key for you to be able to check your work. Make sure you're always attempting these problems on your own before you take a look at any answer key. You're building your critical skills as you do that. And then you're using the answer key as a way to check to ensure that you really understand fully how to answer these questions. Once again, there's another FRQ. You're practicing your geometric shapes. There's 3 all the way to FRQ number 3, moving on to the next page. We'll go over polarity now. Polarity is dependent on 2 factors. The bond polarity with the dipole moment itself, we call that the dipole moment based on the unequal sharing between atoms. And then also the geometric shape, which you have reviewed already using the VSEPR theory. those two items will help to contribute to understand the whole polarity of the molecule. So we're still looking at a covalent compound, so it's the polarity of a covalent compound. There are polar molecules and then there are nonpolar molecules. Polar molecules are polarizable, which means they have an unequal sharing of electrons, and so there's a net dipole as a result of an unequaling sharing of electrons. And usually what happens is the electrons are hanging around the more electronegative atom, and that will cause a partial negative charge on that atom that's more electronegative. And of course, away from the electron will be moving away from the lesser electronegative atom, which means you have a partial positive. Usually, a structure that's polar, we like to use the symmetry to guide us to the polarity, and symmetry along a bond. So if you look at this, here I have, I'm going to draw a line of symmetry right here, and I'll draw it in yellow so you can see my line of symmetry. So here's my axis of symmetry, and you'll notice that there's no mirror image between the left and right side of that axis of symmetry. And so this structure is considered asymmetrical. Okay, so draw a line of symmetry along the bonds, not the lone pairs along the bonded atoms. Okay, I'm going to erase this. Not sure if I could do that. Okay, so now let's go ahead and look at water is polar, obviously. It's asymmetrical. And notice how in water you're seeing that the electrons are really being pulled towards the oxygen. And so that's why the arrow with the partial positive at the tail end of the arrow is shown here. Oxygen is going to carry on a very negative charge compared to the two hydrogen that it's bonded to. Nonpolar substances have no net dipole. So there's no net dipole because the sharing occurs throughout the whole structure of the molecule. So there's equal sharing of electrons. Electrons are spending equal time around all the atoms distributed in the structure. And so it leaves the structure to be symmetrical. So the word, it's usually asymmetrical. You're looking at the line of symmetry. Once again, I'll draw it in, but you'll notice that carbon, this is a tetrahedral shape, and if I draw along, let's see, and I'm going to draw along a whole plane. So say this is a plane of symmetry, you'll see that the structure is symmetrical on both sides of that plane of symmetry. So imagine the symmetry, not a line of symmetry necessarily. Sometimes it's a line if it's a flat structure, but if it's three-dimensional, you're going to do a 3D plane of symmetry. And you'll see that when you draw or you make that plane of symmetry, you'll notice symmetrical structure resulting. Again, I'll get rid of that afterwards so you can see. Alright, what we're going to do, looking at the bonds, the dipole here, there is a slight dipole, not very strong at all, between carbon and hydrogen, because the electronegativity between carbon and hydrogen, I believe, is like 0.4, which makes it polar, but really it's on that borderline of being nonpolar as well. So for our class, for the sake of our class, any CH bond, and I will write this down to be sure, any CH bond is considered nonpolar bond. Make that note. That's a big note for us. So overall, not only is it the CH bond nonpolar, but also the symmetry of the structure. This is a tetrahedral shape, and that symmetry is what allows the structure to be symmetrical and nonpolar. So this is a tetrahedral shape. We're looking at geometry as well as the bond polarity to determine the polarity of the whole substance in the end. All right. What we're going to do is we're going to look at some example problems on number 6. We're drawing the Lewis structure and we're determining whether the structure is polar or nonpolar. We are heavily going to use the symmetry idea to help us, and then we're also going to draw the dipoles in, so the arrows, and also we're going to do both the positive and negative as well as the arrows. Okay, let's go ahead and draw carbon dioxide, and I'm going to do it horizontally because I'm out of room. Start off with carbon. Carbon has 4 valence electrons. There's a little toolbar that's in my way. So there's 2 oxygens, and oxygen has 6 valence electrons. And I really do know that oxygen is not going to bond. The 2 lone pairs that oxygen has is not going to bond. And so I'm going to put them as lines because I know I don't need to split those electrons up to bond in any way. I do my sigma bonds, and then I see that carbon could use more bonds. Both oxygen and carbon are lacking electrons, so I know I'm going to add another multiple bond between carbon and oxygen, and then also between this carbon and oxygen as well. So with this structure, let's go ahead and draw the dipoles in. I'm going to use red as my dipole, okay, my dipole moment. Now oxygen is very electronegative compared to carbon, so electrons are going to be pushing towards the oxygen over there, and then in this bond between the left carbon-oxygen bond, the same is going to happen, making, now notice the positive end, so carbon ends up taking the positive end right here of the dipole, so I am going to see a partial positive and then a partial negative. And that is the structure. Now, even though the bonds are polar, the carbon-oxygen bonds are polar, as we see here, pretty polar, the shape and geometry of the structure is linear. So imagine being pulled this way and then being pulled that way, opposite direction, in a linear 180-degree line. So the opposite pole is going to cancel the other pole, and so the dipoles cancel out. There is no net dipole, so there's not a net dipole as a result because they cancel each other out, these 2 dipoles, and thus the structure, the molecule, is nonpolar in the end. Okay. I'd love for you to try the next one out and describe the polarity. So notice how geometry, both geometry and the bond polarity, so this red stuff is the bond polarity, and then the geometry is the linear shape, tells us whether the structure is polar or nonpolar. Okay, so both bond polarity and the geometry. I'd like you to work through ammonia and methylene dichloride and make sure you draw the dipoles along the way, okay? Let's go over the types of intermolecular forces. Now, intermolecular forces, to remind you, only applies to covalent compounds. So we're only dealing with covalent substances and molecules. Again, you can say molecules to really insinuate covalent. Now, this chart is really a great chart for you to be able to understand the different forces, okay? Now, but I do want to stress something. Dispersion force is also credited to London, a scientist who discovered or studied these different forces. So we oftentimes name this dispersion force London dispersion forces. Okay. Okay. This goes from weak to strong as far as the forces, these different types of intermolecular forces. Let's start off with dispersion forces. There's this great modeling that will help us to understand dispersion forces, and I'll draw over that model to help us to understand it further a little bit more. So all atoms are experiencing this type of force. the London Dispersion Force. And that's because all atoms are made up of electrons. And these electrons will be rotating around the nuclei of any atom or molecule. And when that happens, the electrons at times will shift over to one side. So I'm going to draw those electrons as negative. So negative charge. So this is my negative charge shifted to one side. If electrons are shifted to one side, that will make the this side of the atom, this side of the right side of the atom to be partially positive. So partially negative, partially positive. Now this is very much in an instant that this will happen. The electron shifting over to one side. That will induce another atom to have electrons shifted once again to the left side as well. So here we see electrons shifted to this side, and thus you see an attraction between the atoms. Partial positive on this end, partial negative. There's this level of attraction, weak attraction between these two atoms because of that induced temporary dipoles that are created. So there's a temporary dipole through the shifting of the electrons momentarily onto one side of the structure. Now we know these electrons want to spread out in an atom, so that's why this is such a weak force, because it happens such in like picoseconds, very small time scale. And it's induced in all these particles, okay? It induces another particle to behave that way. Now, unlike these London dispersion forces, which are weak temporary dipoles, and instantaneous, we can also use the word instantaneous as well. So I'm going to add that, instantaneous. It's a good word. Dipoles. Here we get into dipole-dipole forces, which are based on polar molecules. And polar molecules have permanent dipoles. So let's check out the permanent dipoles that occurs in polar molecules. If you look at a molecule like this is actually formaldehyde. This is an example of formaldehyde. Formaldehyde has an oxygen-carbon bond right here, which has a strong dipole, and it's a permanent dipole. That's why it's negative on this side where the oxygen is, and positive on the side where there's hydrogens and the carbon. That will then attract another particle of formaldehyde, and this particle of formaldehyde, the attraction is going to be where the positive end is. So the negative of the carbon-oxygen bond of one molecule is attracted to the positive side of the carbon-oxygen polar bond. And that is what creates these positive partial opposite charges that attract each other between the molecules. Thus, this is between molecules. Notice these are attraction between particles. And this is dipole-dipole. Let's get into hydrogen bonding. Hydrogen bonding is when you see F or N, which are your three most electronegative atoms, attracted or bonded to hydrogen. That bond, any hydrogen attached to any of these three electronegative elements, will create a covalent bond that has a very strong dipole. And that strong dipole, that strength of the dipole, will make this particle quite polar. And this is water, by the way. You can actually see by H2 and O. And so water goes through something called hydrogen bonding. Once again, the oxygens are more negative, and then the hydrogens are where the positive is. And this is true for any water molecule, and so the attraction occurs between the hydrogen end to the oxygen of the adjacent molecule. And so this is an intermolecular force that's quite strong because of the still permanent dipoles, but strong permanent dipoles. So it's even quite strong compared to the dipole type of forces. Okay, now we get to ion dipole. Now ion dipole is made up of those two words. You're looking at an ion right here, and then the word dipole means you're dealing with a polar compound. So the polar compound has a dipole. Usually your polar has a net dipole. And that's why if you mix an ionic compound with a polar molecule or a polar compound, you have this interaction. Here you have a positive cation with water. That water is going to be attracted by the direction of with the oxygen, because the oxygen is where it's negative. So positive and negative attraction. So you're still seeing the opposite attraction, electrostatic attraction occurring, but you're seeing an even stronger attraction because you're dealing with, logically, a fully charged ion, not partial charges like dipoles are, how dipoles are created. So it's a fully charged ion with a polar, a substance that has a permanent dipole. Like water. Oh, it's not dipole. So that attraction, that fully charged ion, is actually so much stronger than any partial, remember these symbols are all partial positive, partial negative symbols, then it's stronger than any partial charge. And so that's why this attraction is even stronger than hydrogen bonding, dipole-dipole, or London dispersion. So that's your overview. Example 7 are all questions around intermolecular forces and intramolecular forces, and then it goes into differences and examples of differences in terms of intermolecular forces. So please work through this. Once again, the answer key is in the subsequent pages. One point to make for this question number 6 here, I think the other questions should be straightforward. But one question to make for actually 5 and 6. Now, when it comes to 5, the more electrons an atom has, and it's nonpolar, specifically nonpolar substances that have no net dipole, the more electrons that atom has or that molecule has, the more London dispersion forces that particle or that molecule will have. And so please be aware that as you answer this question, you'll notice that greater, even though they're nonpolar substances, so they must have London dispersion forces. The London dispersion forces are based on the number of electrons and the dipole that would be created. The dipole would be much stronger with greater number of electrons. We go down to number 6. As you go through number 6, you want to really read it first, and if you can do this before I explain it, great. Pause and let yourself do that, and give yourself the opportunity to try to think through it critically. But if you want to hear the explanation, go ahead and unpause. Take a moment and think about how surface area affects. Now, if you have a linear structure versus a branched structure versus an even more branched structure, you'll notice how the surface area will be different for each of these. Obviously, the one with the greater amount of surface area is going to have better contact between particles. So the stronger the intermolecular forces with other of the same particles. So we're looking at really the forces between other part of the same particle. And this one, since this is a long branch out structure, you're seeing that this structure can easily attract other atoms or molecules of the same structure. It's a long set of problems. Check your answers, don't forget, and make sure you also are able to model. So not only are you working on your explanations, but you're also practicing modeling these structures with one another in terms of the intermolecular forces. Okay. FRQ4, complete it and make sure you check, as well as FRQ5. We're going to get into hybridization after you've completed all of these problems as we move through each of the sections. Okay, what is hybridization? It's a theory. It's a theory that describes the mixing, hybridization of atomic orbitals. Now, recall that the atomic orbitals are your s, p, d, f, g orbitals. And you're going to see that upon bonding, atoms will hybridize their orbitals in order to create equal energy orbitals. And the hybridized orbitals are generated, and they're named these different variations depending on the number of bond sites that could occur to the central atom. So hybridization occurs because the central atoms treats each bond formation equal and is equivalent hybrid orbitals resulting from covalent bonds. Important, the total number of hybrid orbitals by the central atom is equal to the bonding pairs and the non-bonding pairs, so the lone pairs. Pi electrons do not occupy hybrid orbitals, so please exclude hybrid or pi bonds in any kind of hybridization. Okay, and we'll see that when we go through all the different hybridized orbitals. Let's start off with sp. Sp, the hybridization actually can tell us the geometry. So if a substance has an sp hybridized orbital, that substance is linear. This is a perfect example. BeCl2, beryllium dichloride, or beryllium chloride, because it actually has some ionic behaviors as well. But beryllium dichloride because it's covalent as we speak right now. So hybridization is really on the central atom. So we're going to look at the central atom. According to beryllium, if you draw the dot for beryllium, it would look like this. And if you look at beryllium's valence shell, which is the 2s and the 2p, you'll notice that there's two paired electrons, and it does match the electron dot that you see. But how does it explain how beryllium can bond with two chloride ions? Shouldn't you have beryllium with two unpaired electrons so that chlorine can bond, both chlorine atoms can bond? Currently it shows that beryllium cannot bond, but we've seen that beryllium can bond with chloride ions or chlorine atoms. So here we have the hybridization theory helps us to describe the bonding nature, whereas the quantum mechanical theory, the quantum model, doesn't help us to understand how atoms bond in the end. So we're jumping from one model to the next, realizing that one fails to help understand and shed light on the nature, other parts and natures of those substances. In this case, bonding versus the configurations using the quantum model. Now, so what we will do is, in order to represent two unpaired electrons, we're going to hybridize these two orbitals. And by the way, each of these bonds, energy between the beryllium and chloride or chlorine atom is equal in energy, and that's how they discovered that something must be happening on that valence shell with the orbitals, the atomic orbitals, and it must be hybridizing. So we take one electron, move it over to the p, and we hybridize them. We blend them together, and we create what is called sp. Now, how did I get sp? Well, we took one s and then one p, and that's how we made that hybridized orbital. Again, we took one of the s, the 2s, and then one of the p's. So that's why it's called sp hybridized orbital. We don't have to stress the energy level. We know that beryllium has its valence electrons in the second energy level, so we just call it sp hybridized orbital. Now, let's look into sp2. The same thing is going to happen, but now I'm going to talk about unhybridized orbitals and where pi electrons will reside, okay? So pay attention and follow carefully. Here I have carbon, and carbon has 3 sigma bonds, we know. And carbon has one pi bond. So the pi bond I know is going to be on an unhybridized orbital. The sigma bonds are all going to be on hybridized orbitals. So if you look at the geometry around this carbon, you know it's going to be trigonal planar. So we call this an sp2 hybridized orbital, and that insinuates trigonal planar. Let's go ahead and take a look at carbon and what's happening to carbon for this bonding to take place. So carbon normally, as a central atom, it has 4 valence electrons. But now look at this. This would show this kind of dot structure. We know that this is the dot structure that carbon has instead. So how do we account for 4 unpaired electrons that will bond with the carbon over here and the hydrogens and then make another double bond also with the carbon? So 2 of the bonds will be with the carbons and 2 of which will be with the hydrogen. What we do is we move an electron from the 1s over to the 2p, giving us 3 orbitals that are going to be hybridized. So 3 of them are hybridized, but then 1 of them is on an unhybridized orbital. So let's go over to here and see that. So 1 electron goes over here. You'll see sp2 hybridized orbital. There's 3 of them, 1s and 2 p's, but then the other p is going to be unhybridized, so it's going to be just called 2p, and this is your unhybridized orbital where the other carbon will bond, and of course this one of the carbons will bond for the sigma bond, and then another hydrogen will bond here, and then another hydrogen will bond here for the other sigma bond. So there's 3 sigma bonds, 1, 2, 3 for the 3 hybridized orbital. This is your pi bond, and hopefully you can see the relationship between the word pi and p orbital. So this is where our pi electrons come in, because it's on an unhybridized p orbital. Now I didn't mean to cross it out, but this is a description of basically what we just described. Hopefully you can understand this idea of hybridization. The more we go over these different hybridizations, the more it just brings to light how this all works logically. So the next one is sp3, and it's the shape that you'll see from sp3 is a tetrahedral shape because there's 4 hybridized orbitals and 4 bonding sites here. And then CH4 is what we're going to use. We're using methane, and once again carbon is the central atom and it behaves the same way as up here. Carbon, it looks like there's only 2 possible bonds that can take place, but we see that methane exists with 4 possible bonds here to the hydrogens. So we're going to hybridize. We're going to hybridize to create the 4 carbon-hydrogen bonds. So carbon will have 4 of its valence electrons on an sp3 hybridized orbital, because we're going to need to take this electron, jump it over here, and we're going to mix these 2 orbitals to make an sp3. By the way, you can't go beyond s3 here for the p, because there's only 3 orbitals, atomic sublevels for the p orbital. So you're actually going to move into the d after you finish up with 3 hybridized orbitals in the p. So as a result, you're going to see 4 electrons placed unpaired here, and once again each of the hydrogens will bond right at each of these sites to make the bonding sites around carbon. And a reminder, just always going back to why this theory came about. This theory came about with the understanding that if I broke this bond right here between carbon and hydrogen, broke this bond, broke this bond, and broke this bond, they all should be equal energy bonds. And this does not show that. This actually shows that two of the electrons are on higher energy than these two. And it doesn't even show possible 4 bonds here. This shows equal energy and the possible 4 bonds that hydrogen will for the 4 hydrogen atoms. So hybridization is really an important theory in bonding for us to understand how when we broke those bonds, we actually realized that there were equal energy bonds, thus equal energy hybridized orbitals. All right, now we go to sp3d. Once again, there's only one s, there's 3 p's, but there's 5 d's. So now we get, since we're filling up the s and the p already, and they filled up max, now we get into the d orbital. And the d has 5 spots here. Okay, so the shape that arises from this hybridization is trigonal bipyramidal. And a perfect example here we're using is P and the 5 Cl atoms that are bonded to P. P has 5 valence electrons. According to what we see here, this does really match up, but it doesn't match up to what we would expect to happen here in the bonding. A lone pair up here means that electron is not going to bond. It's already paired up. So how is it possible that we can add 2 more chlorine bonds here, atoms to bond? So it must be hybridization that describes that and explains it. So we're going to take this electron, bring it over to the D. Now we have 1 S, 1, 2, 3, 3 P's, and 1 D. So that's why you're seeing sp3d. I'll write this one in. I didn't write the other ones, but again, 1 and 1. So you're seeing 5 hybridized orbitals. 3 of the P plus 1 here for the S and 1 for the D. 1, 2, 3, 4, 5. 5 it is. And that will allow the 5 chlorine atoms to bond at each of these bonding sites for phosphorus. Once again, we're doing hybridization for the central atom and how they bond, or how that central atom will bond with the bonded atoms. We can keep on going. This next one is sp3d2. It's an octahedral shape. And so the example that we're looking at is sulfur with 6 fluoride, so hexafluoride. Now, sulfur looks like this. Once again, if you look at the quantum model, you wouldn't expect 6 fluorine atoms to be able to bond. You'd only expect 2 bonds of fluorine atoms, but there's 6 possible to make SF6. So we have to hybridize. Hybridizing means having to pull 2 of the electrons and moving it into the d orbital. I forgot to put d orbitals. I'm going to go ahead and do that right here. Squeeze in. And of course, I'm going to move 2 electrons in this 3d orbital. So moving that. Now I'm using 2 of the d orbitals. Thus, the hybridization is S1, 3 of the P's, and 2 of the D's. So that is your sp3d2. And that will then allow our 6 fluorine atoms to bond at each of these unpaired sites that you see. Alright, what I'd like you to do is work through the hybridization for the rest. But I'm going to do A first, especially since A has a lone pair. And that you haven't really come to understand whether lone pairs occupy hybridized orbitals or unhybridized orbitals. I'm going to tell you that they occupy hybridized orbitals. And that's why lone pairs cause repulsion, and they really, lone pairs configure into the geometric shape. In other words, they do affect and impact the molecular geometry. So this is ammonia. And how I do this, and I want you to understand my methodology of counting hybridization. I know that this here, lone pair, is going to take up 1 hybridized orbital. Here's another one. Here's another one, and here's another one. So I need 4 hybridized orbitals, and I'll even draw it for nitrogen so you can see. So because there's 4 hybridized orbitals that I need, this is going to ammonia, the nitrogen in ammonia is going to be sp3 hybridized orbitals. Once again, if you want me to draw it, I'll be happy to draw it. Nitrogen is going to have 4 hybridized orbitals called sp3. Now, one of them is a lone pair, so you're going to see this one, and it doesn't matter where you put the lone pair. You could have put the lone pair in the middle if you wanted to, because these are all equal energy. So there's not one orbital is not going to hybridized orbital is not going to be more energy. So the lone pair is occupying a hybridized orbitals, or a hybridized orbitals. So lone pairs occupy hybridized orbitals, whereas pi electrons do not. I do want to apologize. I should go back up here to explain how hybridized or pi electrons work. So here you have all the sigma bonds between hydrogen and carbon, or carbon and carbon right here. How the double bond works, or the pi electrons bonding together, is that one of the orientations, like 2py of one atom and 2py of the other atom, has an unpaired electron, and so that creates the electrons, allows the electrons to move back and forth in these delocalized areas here, the pi bonds. In the pi orbitals, and that is where the pi bond occurs. So this orientation is a single orientation, and that's where the pi electrons are hanging out between the atoms, okay? In this one orientation. If it's a triple bond, then there would be another pi bond that is engaged, that's unhybridized and engaged in bonding between the atoms. Okay, sorry about that. I should have discussed it earlier, but hopefully you got that idea coming back to it. Go ahead and do the rest. Work through B and C. I'll go ahead and show you how to do sulfite ion. F, letter F. So we're really going to address F together. You should be able to work through the rest though, but sulfite ion I'm just going to walk you through once again. Starting off with the central atom, sulfur. Sulfur has 6 valence electrons. Oxygens. Now I know that I'm going to occupy the valence, or the 2 of the oxygens. I definitely know where to place them. It's where the unpaired electron is. The third one, I'm going to have to break this somehow, this lone pair. So I know that that's what I'm going to do. Once again, I'm going to draw 6 valence electrons, and I'm going to draw, for oxygen, I get a little creative and draw oxygen in the shortcut manner. Alright, so I know I'm going to make a single bond here, single bond here, single bond here. I know I'm going to add electrons. How many electrons am I going to add according to what I see up here? I'm going to add 2 electrons to the structure. So I add it right at this time and spot. And I know I'm going to add the electrons on oxygen somewhere. And I'm going to decide, instead of adding the electrons on this oxygen, where I can see a possible double bond, I'm going to add it to the other 2 oxygens, okay? So 1 electron here and 1 electron here. I can see a possible double bond, that's why. Again, you're always taking notice of the possibilities of bonding, okay? So here's my formal charge. Here's another formal charge. I know it because I've added 2 electrons to that structure. And then I see that the best thing to do, instead of trying to move this electron over to this atom, even though oxygen's more electronegative, that would cause sulfur and oxygen to have formal charge. And in a structure with a bunch of formal charge, it's not stable. So you want to do a double bond instead. And this actually can happen because um, sulfur can have an expanded octet. Expanded octet. Okay. Now, hybridization. Once again, I'm going to walk you through how I look at hybridization. I know that lone pairs take on hybridized orbitals. Here's another one that I need, so that's 2. Here's another one, 3, and this other one, 4. This pi electron is on an unhybridized orbital. So I need a total 4. And because it's 4, that will result in sp3 for sulfur. That's why this shape and geometry is rooted in a tetrahedral shape. So this structure actually has a tetrahedral shape with a lone pair, which means it's trigonal pyramidal. So this structure is trigonal pyramidal with its root shape of a tetrahedron. All right, go ahead and keep on working through this and practice, please. It's very important to make sure you practice the structure, or this idea. And of course, complete your FRQs. You're working through all your FRQs, practicing, explaining, as well as drawing your Lewis structures. This will end at FRQ 11, so it's a long stretch of homework. Work through it. So here we finally end covalent bonding. So covalent bonding has a lot of properties. Hybridization, it has formal charges that we have to look at, Lewis structures that we have to draw, and then we got into the they think of all the intermolecular forces versus intra. So covalent compounds have intermolecular forces that guide a lot of their chemical properties. We get into ionic. Ionic is quite simple. Ionic goes into Coulomb's law, and really it's lattice energy that we're looking at when it comes to ionic. So let's go through what an ionic bond is. An ionic bond is transferring of electrons from a metal cation to an anion, non-metal anion. Ionic compounds have this regular repeating patterns of cations and anions in their macrostructure. So look at the very first page of our notes and you should see the macrostructure of an ionic bond or a compound. They're electrically neutral simple ratios called formula unit. So NaCl is the formula unit of this simple whole number ratio that occurs between the ions. Again, NaCl. This is our formula unit. This is what our formula unit looks like. Ions are strongly bonded because they're fully charged particles that are oppositely attracted to one another. So ions are always bonded with a cation and an anion, opposite charges. They tend to be solids at room temperature. They are high melting and boiling points, oftentimes, because they have these intramolecular forces. So ionic bonding is bonded intramolecularly, thus it's a rigid solid. Write that in. They do not conduct electricity unless they have been melted. So molten means melted. And then they're good conductors of electricity because the ions are freed up and the electrons can pass through their, specifically the metal's empty valence shell, because the metal has lost electrons, whereas the nonmetal gained. So there's no room on the nonmetal end, but the metals are the better conductors in an ionic bond that has been melted. Now, if you dissolve also an ionic compound, because ionic compounds are charged ions with partially charged polar water molecules. They're attracted to each other, and they're attracted through what are called ion dipole forces. The lattice energy of ionic compounds are based on Coulomb's law. And lattice energy is basically the energy in the formation of an ionic solid from their gaseous ions. So there's energy release, and that energy is called lattice energy. According to Coulomb's law, the smaller the ion or the greater the charge, the stronger the force of attraction between the ions. Now, charge in this case would be the actual charges on the ions, okay? So now we're not getting into Zeph per se, we're actually getting into the actual overall charge of the ions. The higher the lattice energy indicates higher boiling point and melting point. That's the abbreviation. Charge has a significant impact over size. So charge is going to have a greater impact than the distance in ionic compounds. So let's go ahead and see which one will have the largest negative, because energy is released when you create these ionic compounds. So you're creating which one has the largest negative lattice energy. So means held strongly together. So which one has a strong hold between the ions? Strong force. Between ions. And so let's look at it conceptually according to Coulomb's law. Don't forget Coulomb's law. It's always our go-to law for a lot of even through intermolecular forces, it's actually the law that helps to guide us. Particles that have stronger charges, permanent charges, versus temporary charges like dipole-dipole or hydrogen bonding, or even ion dipole forces, those are all permanent charges, are going to be stronger in force of attraction than weaker charges like London dispersion. So we're seeing Coulomb's law play out. The only thing that's a little an anomaly is the London dispersion forces, and how the more electrons you have, the stronger the intermolecular force. But you can actually, if you understand how London dispersion forces are created, you can actually logically understand why more electrons lead to stronger forces. Anyways, that was a sidetrack. It's okay. I get sidetracked, distracted, so that you can kind of we're trying to bring back Coulomb's law and how it is an overarching theme for this whole class. Okay. All right. Between the two, they both have chloride ion. The difference is the potassium and the lithium. Obviously, the charges aren't different. +1, +1. So we're going to have to go by the sizing. It looks like potassium is larger than lithium. There's going to be a tighter bond here. So the compound that has the largest lattice energy, or the most negative lattice energy, is going to be the one that easily is created in terms of bonding, ionic bond. Okay, and the answer is here, lithium chloride. And that's because lithium chloride is a smaller ion. This part. The potassium is a larger ion, so the force is weaker. Now we go to magnesium, the second example. The second set of example is with magnesium oxide versus lithium chloride. Find them on the periodic table right now. You got to look at them in the periodic table so you can know where they're situated and how to look at them. So yeah, it looks like magnesium is right next to our third energy level. Lithium's second, chloride's third. Oh, so we got a third and second. So they kind of contradict, but really remember how we went back and we said that charge is going to have a greater impact when it comes to lattice energy and ionic compounds. We're going to look at the charge as the predominant effect. So magnesium and oxide has greater charges. So higher charges lead to stronger force. What I'd like you to do is work through these conceptual questions with respect to lattice energy and melting point as well. Remember that the stronger those particles are held together by forces of attraction, you will see the higher the melting point as well as boiling point. And so you're going to have to go through these and make sure all of Coulomb's law applies to these questions. Practice answering these conceptual questions. All right. As small as ionic bonding is as a topic in this unit called chemical bonding, metallic bonding is even smaller. So metallic bonding is metals with metals, and they're bonded through delocalized electrons in what is called an analogy. The analogy they use is a sea of electrons. And usually it's a metal cation with surrounding electrons. So you don't see the electrons right now. I'm going to go ahead and add those electrons in. So these electrons are moving and they're delocalized. And I'm going to show the delocalization by the arrows, okay? Delocalization. Now, why is this possible? Well, metals, if you recall, are on the left side of the periodic table and down below. So that means metals tend to have a low Zeph and a lot of energy levels, so a great amount of distance. So that means metals have a very weak nuclear charge, a weak force from the nucleus to its valence electrons. And with that, that means that these electrons can easily delocalize, move apart from the metal ion itself. And when that happens, thus the metals are considered, this actually brings about a lot of properties, like metal can conduct electricity as well as heat. Now, remember that electricity, and I'm going to draw the best I can, lightning. So here's my lightning bolt. And remember that my lightning bolt is made up of electrons. So my electrons can easily flow through here when I plug or when I conduct electricity, when my metal conducts electricity. So electrons can easily flow through when you plug, and that's why metals are used as the conductor of electricity. When you plug in, if you cut off a wire, you'll see metals wrapped around inside the wire because metals are used for that conduction of electricity. So this is my lightning bolt, or my my electrical outlet. That I'm sending through this piece of metal. And notice how the electrons can flow right easily through, along with the delocalized electrons that are already there. Metals are malleable, so when I try to hammer this piece of metal, you'll notice that because of these delocalized electrons, these metal ions, cations, you'll notice that they can easily move and shift quite easily. Okay. Alloys. Alloys are atoms in pure metal solids, and they are basically mixtures of different metal solids with other atoms. There's two types of alloys. I do want to make sure I finish up. The valence electrons of metal atoms are not tightly held and exist as sea of electrons, occupying interstitial space. So these empty spacing between the metal and the core. This atomic structure accounts for the metal's conductivity and other properties, which we just described. Alloys are mixtures of metals with other metals, or metals with other non-metals as well. But there's two types of classification of alloys, and let's go ahead and look at the graphic organizer for that. So the mixtures and blends to make an alloy are actually heated up to basically melt and blend those constituents, metal atoms with whatever other metal. And then, of course, cooling occurs to produce the alloy. Now, sometimes we create alloys for many different purposes. Sometimes it's to strengthen the metal. Sometimes it's to allow for more conductivity for the metals. So let's take a look at what AP will address. There's two types of alloys that you will need to know. There is a substitutional alloy, and that's when you take constituents that have similar atomic radii, and then you replace it and substitute it into the crystal lattice structure of that metal, of another metal. So here's one type of metal, and then you're replacing. So these shaded little round circles are really the replacement of similar size. Notice how this is the original metal, and then you're substituting another metal in for the same similar size. And a perfect example would be sterling silver. Sterling silver is used with a lot of silver. So the main component is silver, and then they substitute it with copper, and silver and copper are similar in size, and so that's so there's a substitution with some of the copper or the silver with the copper atoms. Brass is another example. Much more of brass is contained with some of the substitutes. So 40% is zinc and 60% is copper. Now we get to interstitial. Interstitial is different from substitutional because now you're substituting with different atomic radii. So you'll notice smaller, oftentimes smaller, that fits into the interstitial spaces and holes of the lattice structure of the metal. So here you have the metal, and these little dark solid circles are your interstitial atoms, and usually you're just fitting it in the empty space. So you're not substituting it, you're just fitting it into empty spots where there's empty spots, the interstitial spaces. So this ends the unit. So we've discussed, just to take a step back, we've discussed covalent bonding, we've discussed ionic bonding and metallic bonding, but we've never discussed covalent network, and that's because covalent network is actually put and placed under covalent. However, covalent network would be diamond. Covalent network would be your really hard surface particles that are bonded through a network, like multiple atoms, and it's continuously bonded. So it's not it's not a bond type that is stressed in our class, AP class, though I like to have it added as a way for you to see the big picture of bonding in this class. Go back to page 1, I highly recommend, or page 2, and look at the 4 types of bond and kind of go through and run through all the characteristics of the 4 types of bonds as an overarching understanding of this whole unit.